The night of January 3rd, 1945, Mindoro Island, Philippines. Technical Sergeant William Henshaw stood in the humid darkness next to a 6-foot radar dish mounted on a trailer, watching the green phosphorescent sweep paint circles on the screen in front of him. The SCR-584 had been tracking empty sky for 2 hours. Then, 23 miles out, a single contact appeared, range decreasing, bearing 180, altitude 4,000 feet, coming straight toward the American beachhead. The Japanese pilot flying Zero probably believed darkness made him invisible. He was wrong. What he didn't know, what no Japanese commander yet understood, was that the Americans had deployed a weapon system that turned night into an irrelevant variable. The SCR-584 could see aircraft with precision that made searchlights obsolete. When paired with the M9 Director and 4 90mm guns, it created something Japanese aviators had never encountered before. Anti-aircraft fire that tracked targets automatically and hit what it couldn't see. 20 seconds after that radar contact appeared, 16 90mm shells ripped through the darkness at 1,500 feet per second, their proximity fuses waiting. The Zero disintegrated at 3,000 feet, scattered across a quarter-mile of empty jungle. No searchlights, no optical sighting, just invisible microwaves, analog computing, and mathematics that transformed defensive gunnery from an art into a science. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By January 1945, American forces understood they faced a problem that conventional anti-aircraft defenses couldn't solve. Kamikaze attacks had killed more sailors in 3 months than the entire pre-war Pacific Fleet had lost in training accidents over a decade. Ships burned, men died, and Japanese pilots kept coming, accepting certain death as tactical doctrine. During the Battle of Leyte Gulf in October 1944, organized kamikaze strikes sank the escort carrier St. Lo and damaged 3 others in minutes. The mathematics were simple and horrifying. Conventional anti-aircraft fire required roughly 20,000 shells to bring down a single aircraft. Against kamikazes, who didn't care about taking damage that would force normal pilots to abort, even that ratio looked optimistic. The United States Navy had developed the most advanced shipboard anti-aircraft systems in the world. The 5-inch 38 caliber gun with the Mark 37 fire control system could throw up defensive barrages that shredded conventional attacks. 40mm Bofors guns filled the medium range. 20mm Oerlikons created walls of lead at close range. None of it mattered enough. A kamikaze attack could be repelled only by damaging the aircraft so severely it was forced off its attack trajectory. The Oerlikon proved inadequate for this task. Even the Bofors didn't always disintegrate the aircraft in time. And at night, when Japanese pilots could approach under cover of darkness, optical fire control became nearly useless. Ground-based anti-aircraft defenses faced identical challenges. Army batteries protecting invasion beachheads and forward airfields used 90mm guns, powerful weapons capable of reaching 40,000 feet and firing up to 20 rounds per minute. But hitting a fast-moving target required knowing exactly where that target was, where it was going, and precisely when to fire so the shell and aircraft occupied the same point in space at the same moment. Human gunners working with optical rangefinders and mechanical predictors couldn't calculate fast enough. By the time they'd computed a firing solution, the target had moved. At night, they fired blind, hoping searchlights would find targets or that proximity to the radar's general bearing might produce results. The radar systems available in early 1944 couldn't bridge this gap. The SCR-268, America's first fire control radar, used long wavelength signals that provided rough range and bearing but lacked the precision needed for accurate gunlaying. One of these radars had detected the incoming Japanese strike force at Pearl Harbor on December 7, 1941. The operators had seen the contact. They just couldn't tell headquarters exactly how many aircraft were coming, at what altitude, or precisely where they'd arrive. Another SCR-270 had tracked Japanese bombers approaching Midway on June 4, 1942, giving defenders warning but not the targeting data needed to destroy every aircraft before they reached the island. What was needed wasn't just detection. It was precision tracking accurate enough to automatically lay guns on target, coupled with computing power fast enough to calculate firing solutions in real time, combined with ammunition smart enough to detonate at the optimal moment even if the shell missed by 70 feet. The technology for each component existed separately by 1940. Making them work together as an integrated system required solving problems that most military officials considered impossible. The story began in September 1940, when a British delegation arrived in Washington, carrying secrets their government believed might save them from Nazi Germany. The Tizard mission, named for Sir Henry Tizard, who led it, brought American scientists a device called the cavity magnetron. This small object, about the size of a hockey puck, could generate microwave radar signals powerful enough and precise enough to detect aircraft at 40 miles and track them with accuracy measured in yards, not miles. British scientists had invented it 8 months earlier. They couldn't manufacture it in the quantities needed for war. American industry could. Vannevar Bush, heading the National Defense Research Committee, grasped immediately what the British were offering. This wasn't just better radar. This was the foundation for an entirely new approach to air defense. He established the Microwave Committee and tasked MIT with creating a laboratory to develop practical applications. By December 1940, the Radiation Laboratory at MIT was operational, staffed by some of the most brilliant physicists in America. Their mandate was urgent and explicit: develop microwave radar systems that could detect, track, and help destroy aircraft before those aircraft destroyed Allied forces. Among the projects assigned highest priority was a gun-laying radar that could automatically track fast-moving aircraft and feed targeting data directly to anti-aircraft batteries. The existing SCR-268 couldn't provide fire control quality data. Its long wavelength meant target positions were approximate. Against aircraft traveling 300 miles per hour, approximate wasn't good enough. The Rad Lab team, overseen by Lee Davenport, began designing a system that would use the British magnetron to create a microwave radar accurate to 0.06 degrees. 1 mil, precise enough to place guns on target automatically. The technical challenges seemed insurmountable. The radar needed to track moving targets continuously, which meant the antenna had to follow the aircraft automatically, not wait for human operators to manually adjust its position. The system used something called conical scanning, where the radar beam rotated around the antenna's central axis to find maximum signal strength, constantly adjusting to keep the target centered. This wasn't new. German Würzburg radars used it. But the SCR-584 would develop the concept much further, adding fully automatic tracking driven by motors mounted in the antenna's base. For detection, the system included a helical scanning mode that let operators search for aircraft across the sky, a dedicated PPI display, a circular screen showing range and bearing like a plan view map, made interpretation easy. When used in search mode, the antenna spun at 4 revolutions per minute while nudging up and down to scan vertically. Once a target was detected and within range, operators could lock on. From that moment, the radar tracked automatically, following the aircraft wherever it went with precision no human operator could match. The system operated at 4 frequencies between 2700 and 2800 MHz, 10 to 11 cm wavelength, sending out 300 kilowatt pulses, lasting 0.8 of a microsecond, with a pulse repetition frequency of 1,707 pulses per second. It could detect bomber-sized targets at roughly 40 miles range, and generally track them automatically at about 18 miles. Accuracy within this range was 25 yards in range and 0.06 degrees in bearing. The electrical beam width was 4 degrees, wide enough to capture the target even when mechanical pointing wasn't perfect. The Rad Lab had a prototype running by April 1941. To test the automatic aiming system, they attached the radar's outputs to a gun turret taken from a Boeing B-29 bomber, removing the guns and replacing them with a camera. On May 31, 1941, a friend flew his light plane around the area while the system tracked it automatically, the camera recording every second. The footage proved the concept worked. Work then started on making the system suitable for field use. mounting everything in a single trailer with the 6-foot antenna on top. Known as XT-1 for Experimental Truck 1, the system was first tested at Fort Monroe in February 1942. But the radar alone wasn't enough. Someone had to translate the radar's detection into firing commands that would actually point the guns and trigger them at precisely the right moment. This required computing power beyond anything mechanical systems could provide. The calculations were staggering in complexity. Course and speed of incoming aircraft, shell velocity and fuse timing, powder temperature affecting propellant burn rates, shell drift caused by spin, air density at various altitudes, wind speed and direction. All of this had to be computed continuously, updated every fraction of a second as the target moved, then converted into electrical signals that would drive servo motors, positioning 4 separate 90mm guns simultaneously. David Parkinson, an engineer at Bell Labs, had been thinking about this problem for months. In May 1940, he had a dream about being in an anti-aircraft emplacement where he spotted a potentiometer, a variable resistor used to control electrical circuits. When he woke, he spent 2 weeks working with his boss to draft specifications for an analog computer that could provide firing solutions for anti-aircraft guns. Bell Labs, led by Harvey Fletcher and Mervyn Kelly, submitted the proposal to the National Defense Research Committee later that year. The project was approved in December 1940. Development proceeded under Drs. David B. Parkinson and Clarence A. Lovell. The resulting device was the M9 Gun Director, an analog computer that continuously calculated trigonometric firing solutions for anti-aircraft weapons. It received target range, bearing, and elevation from the radar. It calculated where the target would be by the time shells reached it. It adjusted for dozens of variables affecting shell flight. Then it sent electrical commands directly to servo motors that traversed and elevated the guns automatically. The M9 had 4 sets of outputs, allowing a single director to control 4 90mm M1 guns simultaneously. The entire system, including the M9, was demonstrated in complete form on April 1, 1942. A contract for over 1,200 systems arrived the next day. The third component of what would become known as the anti-aircraft triad was already in development, driven by a separate branch of the National Defense Research Committee. Merle Tuve at the Carnegie Institution had been working on proximity fuses since early 1940, trying to solve a problem that had plagued anti-aircraft artillery since the First World War. Conventional shells detonated based on time fuses set before firing, altimeter fuses triggered by air pressure changes, or impact with the target. All 3 methods were wildly inefficient. Time fuses required perfect range calculation. Altimeter fuses worked only if the target flew at the altitude gunners predicted. Impact fuses required direct hits. British calculations from the Battle of Britain showed conventional time-fused shells hit their targets less than 2% of the time. Tuve envisioned something revolutionary, a miniature radar packed into the nose of an artillery shell that would sense when it was close to a target and detonate automatically at the optimal moment for maximum destructive effect. This seemed impossible by every conventional measure. Artillery shells travelled at tremendous speeds, endured accelerations of 20,000 G-forces, and spun wildly through the air. Electronics required delicate vacuum tubes the size of light bulbs, heavy batteries, and careful calibration. Vacuum tubes shattered when dropped from table height. Radio sets weighed hundreds of pounds. The idea of combining these incompatible technologies violated everything engineers understood about both fields. But Tuve possessed an intimate understanding of both radio wave propagation and the mathematical principles governing explosive shells. His pre-war research had focused on atmospheric phenomena and radio astronomy, work that required building sensitive electronic instruments capable of detecting the faintest electromagnetic signals. He knew that radar worked by bouncing radio waves off objects and measuring the return signal's timing. He knew that proximity meant precision. A shell that could sense when it was close to a target could turn near misses into effective kills without requiring perfect accuracy. Through 1940 and early 1941, Tuve's team at Section T, a classified research division funded by the National Defense Research Committee, methodically attacked each technical obstacle. They experimented with miniaturized vacuum tubes, testing components against increasingly severe conditions. They worked with specialty manufacturers to develop new battery chemistries that could activate reliably under extreme acceleration. They investigated novel materials for protecting delicate circuits from shock, vibration, and temperature variations that ranged from Arctic cold at altitude to desert heat on the ground. Progress came in small increments, measured in improved survival rates and longer operational lifespans for test components. Then Pearl Harbor happened. On December 7, 1941, as Japanese aircraft devastated the Pacific Fleet, American anti-aircraft gunners fired desperately at targets they could barely track. Their time-fused shells exploded harmlessly in empty air, while enemy bombers completed their attack runs unmolested. Worse, many American shells fell back to Earth unexploded, killing civilians in Honolulu neighborhoods miles from the harbor. The horrible irony was undeniable. American defensive fire posed nearly as much danger to American citizens as it did to Japanese attackers. The attack on Pearl Harbor transformed everything. Tuvey's Section T got unlimited funding and a single mandate: solve the unsolvable or watch the war be lost. By April 1942, the proximity fuse was ready for testing at the secret Applied Physics Laboratory in Silver Spring, Maryland. The design was elegant and compact. A plastic nose, transparent to radio waves, covered the receiving antenna. The shell itself constituted one electrode of the dipole, with the fuse as the other. 4 miniature vacuum tubes, each the size of a fingertip and rugged enough to survive firing, emitted a steady oscillating 180 to 220 MHz signal. Any metal object detected within a few megahertz of the pulse triggered the detonator. After successful tests, Sylvania Corporation began producing the fuses at 400 per day in early 1942. By late 1944, Sylvania and other companies were mass-producing 70,000 of them daily in various calibers. The technology that most experts had declared impossible was now rolling off assembly lines faster than gunners could fire them. The anti-aircraft triad was complete: the SCR-584 radar to detect and track targets with precision, the M9 director to compute firing solutions automatically, proximity fuses to detonate shells at the optimal moment. Together, these 3 technologies would transform anti-aircraft warfare from a numbers game of probability into a lethal science of certainty. But first, they had to reach the battlefield. The radar was intended for introduction in late 1943, but delays meant the SCR-584 didn't reach field units until early 1944. The first combat deployment came at Anzio in February 1944, where it played a crucial role breaking up Luftwaffe concentrated air attacks on the confined beachhead. German bombers had been jamming the earlier SCR-268 radars and bombing the beachhead at night with near impunity. On the evening of February 24, 1944, 4 American 90mm guns controlled by an SCR-584 and M9 director opened fire on a flight of 12 Junkers Ju-88 bombers. They shot down 5 in minutes. The success achieved that evening dramatically reduced German nighttime bombing from that point forward. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The system's most famous success came against German V-1, flying bombs launched against southern England, starting in June 1944. The V-1 was a 27-foot-long pilotless ramjet missile that flew at more than 320 knots, too fast for propeller-driven fighters to catch unless they dove from altitude. It flew in a straight line to crash and detonate nearly a ton of amatol explosive on whatever target lay below. The British called them buzz bombs for the distinctive sound of their pulse jet engines. German engineers launched them from rails in occupied France, aiming them at London with crude guidance systems that simply cut the engine after a predetermined flight time. When the engine stopped, the bomb fell. Royal Air Force and US Army Air Force fighters could intercept and shoot down buzz bombs, but there were too many to stop by fighters alone. Ground-based anti-aircraft fire became the primary defense. The problem was shooting down enough of them. During the first week, V-1s entered the coastal gun belt, protecting southern England. Anti-aircraft batteries destroyed 17%. Gunners were firing using optical sights and the older SCR-268 radars that couldn't provide precise enough data for consistent kills. Then the SCR-584 units arrived, with their associated M9 directors and proximity-fused ammunition. The transformation was immediate and dramatic. By August 23, 1944, anti-aircraft batteries were destroying 60% of all V-1s entering the coastal gun belt. In the last week of August, the rate jumped to 74%. On one extraordinary day, 82% were shot down. The rate of ammunition expenditure told the real story. It had dropped from 1 destroyed for every 2,500 shells fired, to 1 for every 100 shells. On August 28, the last day Germans launched V-1s, before Allied troops overran their launching sites, 104 were launched. The SCR-584 controlled guns shot down 64. Fighters accounted for 14 more, only 4 reached London. In all, anti-aircraft batteries shot down 1,600 V-1s, about the same number as fighters. The SCR-584 had been one of the Rad Lab's biggest gambles. It turned out to be one of their greatest successes. But the system's most critical test was still to come. In the Pacific, where American forces were pushing toward the Japanese home islands, a new threat had emerged that would require every advantage the SCR-584 could provide. Japanese military leadership had reached a desperate conclusion by October 1944. Conventional aerial combat against American forces was unsustainable. Japanese pilots lacked the training of their early war counterparts. American fighters dominated the sky. American anti-aircraft fire from ships had grown increasingly effective. Traditional bombing and torpedo attacks achieved diminishing results while costing aircraft Japan couldn't replace, and pilots it couldn't train fast enough. Something had to change. Vice Admiral Takejiro Onishi, commanding Japanese naval air forces in the Philippines, made a proposal that shocked even hardened military commanders. Organized suicide attacks. Pilots would deliberately crash their aircraft, loaded with bombs and fuel, directly into American ships. 1 aircraft, 1 ship. The mathematics were brutal but undeniable. Japan was losing the war of production. America built ships faster than Japan could sink them through conventional means. But if every sortie guaranteed a hit, if every pilot who flew accepted his death as certain, then maybe the mathematics could be reversed. Maybe American losses could reach levels that would force negotiation rather than invasion. The first organized kamikaze attacks occurred during the Battle of Leyte Gulf in October 1944. On October 25th, a Zero crashed into the escort carrier St. Lo. The ship exploded and sank within minutes, taking 108 crew members with it. 3 other escort carriers in the same group were damaged. American sailors watched in disbelief as Japanese pilots deliberately flew into ships, accepting certain death to ensure hits that conventional attacks couldn't guarantee. The psychological impact exceeded the physical damage. American defensive fire that had been optimized to drive away attacking pilots, forcing them to abort or miss their targets, became largely irrelevant. Kamikaze pilots didn't abort. Damage that would force a conventional pilot to turn back didn't matter to someone who intended to die anyway. The suicide tactics proved horrifyingly effective. During the Philippines campaign from October 1944 through January 1945, kamikazes achieved hit rates 3 to 4 times higher than conventional bombing and torpedo attacks. Traditional attacks resulted in hits roughly 10% of the time. Kamikazes scored hits 29 to 37% of the time, depending on the operation. They sank more ships than conventional attacks while using fewer aircraft. The escort carrier Bismarck C went down on February 21, 1945, after a kamikaze strike during the Iwo Jima operation, killing 318 sailors. The fleet carrier Saratoga took massive damage from kamikaze hits the same day, leaving 123 dead. American fleet commanders faced a crisis. The planned invasion of Okinawa, scheduled for April 1945, would require naval forces to remain exposed near Japanese-held territory for months. Intelligence estimated Japan had preserved thousands of aircraft specifically for kamikaze operations. If suicide attacks continued achieving 30% hit rates against the invasion fleet, casualties would reach levels unprecedented in naval warfare. Something had to break the kamikaze effectiveness, or the Okinawa campaign would become unsustainably costly. The Navy's counter to kamikazes combined multiple layers. Carrier aircraft would strike Japanese airfields, destroying kamikazes on the ground before they could launch. Combat air patrols would intercept attackers as far from the fleet as possible. Radar picket destroyers stationed along likely approach routes would provide early warning while their own anti-aircraft fire engaged targets. And every ship would maintain maximum defensive fire, using the most advanced anti-aircraft systems available. But naval anti-aircraft systems, as sophisticated as they were, faced fundamental limitations, defending against suicide attacks. Ships at sea operated in 3 dimensions. Radar coverage was excellent for detecting aircraft, but less effective for ground-based threats. The 5-inch 38 caliber guns with Mark 37 directors that formed the backbone of fleet air defense were optimized for high-altitude threats and targets at range. Close-in defense relied on 40mm and 20mm guns that required the attacking aircraft to be destroyed before it reached the ship. There was no margin for error. Ground-based anti-aircraft defenses on beachheads and forward airfields faced different challenges but the same fundamental problem. They had to destroy kamikazes completely, not just damage them. A conventional attacker damaged by anti-aircraft fire would typically abort. A kamikaze would keep coming until physically unable to control the aircraft. This meant defensive fire had to be more accurate, more lethal, and more consistent than anything previously required. The older fire control systems weren't adequate. What was needed was the full capability of the SCR-584 radar, M9 director, and proximity fuses, working together as an integrated system against the most difficult targets Allied gunners had ever faced. Priority for SCR-584 deployment had gone to the European theatre through 1944. Production couldn't meet demand across 2 theatres simultaneously. Europe got the advanced systems first because that's where the immediate threat was concentrated. By late 1944, as the Kamikaze campaign intensified, the Pacific began receiving SCR-584 units in significant numbers. These systems would arrive just in time for the bloodiest aerial combat of the Pacific War. General Douglas MacArthur's forces landed on Leyte in the Philippines on October 20, 1944. Japanese air attacks began immediately. Over the next 2 weeks, the combination of conventional attacks and the new kamikaze tactics inflicted serious casualties on American ships supporting the invasion. As MacArthur's forces secured Leyte and prepared to move on Mindoro, closer to Manila, the need for effective air defense at forward positions became critical. Army anti-aircraft battalions would have to protect beachheads and newly constructed airfields, while exposed to continuous kamikaze attacks. The first SCR-584 units arrived at Leyte in late October 1944, deployed with anti-aircraft battalions protecting the invasion force. MIT radiation laboratory engineer Henry Abajian was there, assigned to train gun crews on the new system. What he found disturbed him. Despite having the most advanced fire control radar in the world, crews weren't using it properly. They set up batteries as if they still had to depend on optical gun laying. They were ignoring the automatic tracking capability that made the SCR-584 revolutionary. The problem was psychological and institutional. These were experienced gunners who had trained for years on older systems. They'd developed techniques and instincts that worked with searchlights and mechanical predictors, telling them to trust a radar system that tracked targets automatically, that calculated firing solutions faster than any human could, that required them only to load the guns while the system did everything else, ran counter to everything they'd learned. Many crews had encountered radar before. The SCR-268 had been unreliable, providing approximate data that still required significant human judgment to convert into effective fire. Veterans had learned not to trust radar completely. That skepticism now prevented them from using the SCR-584 to its full potential. Abajian and a General Electric technician toured forward positions, conducting demonstrations to prove the system's capability. At one battery on Mindoro, south of Leyte, Abajian found 4 SCR-584 units controlling 16 90mm guns. They were still not using the system as designed. Abajian connected a set of searchlights to a spare SCR-584 and made a proposal to the battery commander. When the next Japanese aircraft was detected, the guns would fire automatically based on the radar's tracking. Only after the guns fired would Abajian turn on the searchlights. "When we turn on those lights," Abajian told the officer, "I guarantee there will be an aircraft in that beam." The battery commander agreed, though the skepticism in his voice was clear. That night, when the SCR-584 detected the next incoming aircraft, the commander spoke to his gunners over the fire control net. "A battery locked on target. Fire when ready." "Commencing fire," the gunners responded. 16 90mm guns roared simultaneously, muzzle flashes strobing the night sky like fireworks. At that moment, Abajian switched on the searchlights. Sure enough, right in the center of that beam was a Japanese aircraft, exactly where the radar said it would be. A second salvo burst out, proximity fuses detonated. The plane transformed into a bright yellow and orange meteor as it disintegrated and fell to earth. The searchlights followed the burning wreckage all the way down. Cheers erupted from every man in the battery. There, on that dark night in the Philippines, the work of MIT's Radiation Laboratory, Bell Labs' analog computing expertise, and Carnegie Institution's proximity fuse development came together in the most dramatic possible vindication. From that moment forward, no one in that battalion would doubt that radar could do what optical systems couldn't. Word spread. Other batteries requested demonstrations. Training improved. Gun crews learned to trust the system. Over the next 2 weeks following that demonstration, the 6 SCR-584 units that had gone ashore immediately behind the first wave of assault troops brought down approximately 300 Japanese aircraft. General MacArthur sent a message to the anti-aircraft regiment commander: "Superior shooting." Those 300 kills represented the largest concentrated success the system had achieved in the Pacific to that point. More importantly, they established proof of concept under the most demanding conditions imaginable. The SCR-584 worked against fast-moving, low-altitude targets at night. It worked when human gunners couldn't see what they were shooting at. It worked specifically against kamikazes, which required complete destruction to be effective kills. The success at Leyte and Mindoro in late 1944 demonstrated something Japanese commanders didn't yet understand. American defensive technology had reached a point where darkness no longer provided concealment. The night attacks that Japanese forces had used effectively earlier in the war, relying on superior night fighting training and American defenses optimized for daylight operations, no longer offered a significant advantage. An aircraft at night was just as visible to microwave radar as one in daylight, perhaps more so, because the radar didn't care about clouds, haze, or smoke that degraded optical targeting. This technological shift would prove decisive as American forces moved north toward Okinawa and eventually toward the Japanese home islands themselves. The kamikaze threat wasn't diminishing. Intelligence estimates suggested it would intensify as American forces approached Japan. But now, for the first time, American ground-based anti-aircraft defenses had a system that could engage targets they couldn't see and hit them with mathematical precision. The invisible war of electronics and mathematics had begun to override the physical war of tonnage and numbers. And in that invisible war, America held advantages Japan couldn't match. The Battle of Okinawa began on April 1, 1945, and immediately became the most intense aerial combat operation in the Pacific War. The strategic calculation was brutally simple. American forces needed to capture Okinawa as a staging base for the invasion of Japan. Japanese forces understood that every day they held Okinawa was another day. American ships remained exposed to aerial attack. Imperial Japanese Army forces dug into the island's southern highlands, prepared to fight to the last man. Their goal wasn't to win. It was to hold long enough for aerial attacks to inflict unsustainable casualties on the American fleet. The Japanese plan, designated Tengo, Operation Heaven, emphasized massed kamikaze raids called kikusui, floating chrysanthemum. 10 waves were planned, each involving hundreds of aircraft that would saturate American defenses through sheer numbers. Japanese strategists estimated they had preserved 10,000 aircraft for kamikaze operations. Half would be used at Okinawa. The mathematics seemed to favor Japan. Even if American defenses shot down 80% of attacking aircraft, the remaining 20%, hitting ships at kamikaze effectiveness rates, would sink or damage enough vessels to make continued operations untenable. What Japanese planners didn't fully account for was how dramatically American defensive capabilities had improved since the Philippines campaign. The SCR-584 radar, M9 director, and proximity fuse combination that had proven effective at Leyte was now being deployed in greater numbers with crews who understood how to use the system properly. More importantly, the integration between shipboard defenses and ground-based anti-aircraft batteries had improved. Radar picket destroyers provided early warning, combat air patrols intercepted attackers at distance, and ground-based anti-aircraft units protecting the invasion beachhead and newly constructed airfields brought a level of defensive firepower that no previous Pacific campaign had enjoyed. The first Kikusui wave launched on April 6, 1945. 355 kamikazes attacked. They sank 4 vessels and damaged 20 others. The casualties were significant but not catastrophic. American defenses had fired on more enemy aircraft than in any previous single day of the war. The volume of defensive fire was staggering. Ships and ground-based batteries together expended ammunition at rates that would have been impossible to sustain earlier in the war. But the industrial capacity that allowed America to produce 70,000 proximity fuses per day also ensured ammunition supplies remained adequate. Among the ground-based defenses at Okinawa were multiple anti-aircraft battalions equipped with SCR-584 systems. These units had learned from the Philippines' experience. Crews understood the system's capabilities. They trusted the automatic tracking. They'd practiced coordinating with naval units to avoid friendly fire while maximizing coverage, and they'd learned to exploit the system's greatest advantage. Operations. Japanese kamikaze tactics evolved throughout the Okinawa campaign. Early attacks came during daylight, relying en masse to overwhelm defenses. As American fighter coverage and anti-aircraft effectiveness increased, Japanese commanders shifted more attacks to dawn and dusk, when visibility degraded optical fire control, but aircraft could still navigate visually. Then they began launching more night attacks, betting that darkness would reduce American defensive effectiveness enough to improve kamikaze hit rates. It was a reasonable assumption based on pre-1944 defensive capabilities. Searchlights could only illuminate one target at a time and telegraphed their position to every other aircraft in the area. Optical fire control required seeing the target, which meant either daylight or searchlight illumination. Radar fire control systems existed, but the SCR-268 wasn't accurate enough for consistent results. By mid-1945, those limitations no longer applied to units equipped with SCR-584 systems. The night engagements at Okinawa demonstrated what Abajian had proven at Mindoro, but at larger scale. SCR-584 radars detected incoming kamikazes at maximum range, typically around 40 miles for bomber-sized targets. As aircraft closed to 18 miles, automatic tracking engaged. The M9 director computed firing solutions continuously, updating every fraction of a second as targets maneuvered. When aircraft entered effective range, guns opened fire automatically, their crews needing only to maintain ammunition supply. Proximity fuses detonated at optimal moments, creating fragmentation patterns that shredded aircraft even when shells missed the fuselage by 50 feet. The effectiveness rates were extraordinary. Individual batteries reported shooting down Japanese aircraft that they couldn't see with optical instruments, guided entirely by microwave radar tracking targets through darkness. The psychological impact on gun crews was profound. They'd spent years training to visually acquire targets, calculate range and bearing, and fire based on human judgment. Now they watched green dots on radar screens and let computers position their guns while they loaded shells. It felt wrong initially. It violated every instinct, but the results couldn't be argued with. Japanese pilots reported that American anti-aircraft fire at night had become uncannily accurate. Attacks that previous campaigns had shown could succeed under cover of darkness now resulted in aircraft being destroyed before they reached their targets. Some units reported that American guns seemed to predict where they were going, opening fire before the aircraft had fully committed to their attack runs. This wasn't prediction. It was the M9 director calculating target trajectories and leading the target appropriately, firing shells to where the aircraft would be rather than where it currently was. The second Kikusui wave launched on April 11th and continued through April 12th. More than 300 kamikazes attacked. They sank only one destroyer but damaged 19 other vessels. Again, the casualties were serious but not catastrophic. The pattern was clear. Japanese kamikaze tactics could still inflict damage, but not at the rates needed to force American withdrawal. For every ship sunk or seriously damaged, dozens of aircraft were being destroyed, and the rate of attrition was accelerating as American defenses improved through experience. Between the second and third Kikusui waves, American anti-aircraft battalions on Okinawa made adjustments based on what they'd learned. Radar operators refined their search patterns to detect low-altitude approaches more effectively. Directors established better coordination protocols with naval units to deconflict fire zones. Gun crews practiced faster reload procedures to maintain higher rates of fire. The learning curve was steep, driven by the knowledge that every improvement in defensive effectiveness saved lives. The third Kikusui wave on April 16th involved 165 kamikazes. They damaged several ships but sank none. The fourth wave on April 22nd involved 160 aircraft. Similar results, damage but no sinks. The pattern held through subsequent waves. Japanese aircraft kept coming. American defenses kept shooting them down at rates that made the tactic unsustainable. By the time the 10th and final Kikusui wave launched on June 22nd, it was clear that the massive kamikaze campaign had failed to achieve its strategic objective. American forces remained off Okinawa. The invasion proceeded. The losses Japan had inflicted were significant but not decisive. More than 900 ships from the Allied fleet had been involved in the Okinawa campaign. Of these, 36 were sunk and 368 damaged by kamikaze attacks. The casualties were the highest of any naval campaign in the war, but the fleet hadn't withdrawn. Ground-based anti-aircraft defenses had helped ensure that kamikaze effectiveness rates stayed below the threshold needed to force American commanders to reconsider the operation, and the SCR-584 systems had proven themselves against the most intense aerial assault in history. Final accounting for anti-aircraft effectiveness at Okinawa showed that ground-based and shipboard anti-aircraft fire combined had destroyed more Japanese aircraft than in any previous year of the war. More than 50% of all anti-aircraft kills during World War II occurred in the final 12 months, with Okinawa representing the peak of defensive effectiveness. The SCR-584 and its associated systems didn't win the battle alone. Combat air patrols, shipboard anti-aircraft systems, and the courage of sailors and soldiers who maintained defensive fire under suicidal assault all contributed. But the technological edge, provided by microwave radar fire control, proved decisive in preventing Japanese tactics from achieving their intended effect. The statistical analysis revealed patterns that Japanese commanders couldn't fully understand without knowing the technical details of American defensive systems. Kamikaze attacks during daylight achieved hit rates around 25%. Attacks at dawn or dusk achieved slightly higher rates, around 30%. Night attacks, which Japanese planners expected would achieve the highest effectiveness due to degraded American defensive fire, actually achieved the lowest rates, around 20% or less. This inverted the expected relationship between visibility and defensive effectiveness. The reason was straightforward but would have seemed almost magical to anyone who didn't understand radar fire control. Darkness didn't degrade SCR-584 effectiveness at all. The radar saw just as well at midnight as at noon. Better, in some ways, because atmospheric conditions often improved microwave propagation at night. Japanese pilots flying through darkness toward what they believed were concealed approaches were actually flying into kill zones, where American defensive fire was just as accurate as during daylight, perhaps more so because the attacking aircraft couldn't see tracers or explosions that might warn them to maneuver. The transformation in anti-aircraft warfare between 1941 and 1945 was revolutionary. At Pearl Harbor, American gunners fired frantically at aircraft they could barely track, using optical sights and mechanical predictors that couldn't calculate fast enough, expending thousands of shells for each hit, while unexploded shells fell on civilians. By Okinawa, ground-based batteries were destroying aircraft they couldn't see, guided by radar accurate to 1 mil, with firing solutions computed by analog computers faster than any human could calculate, using shells that detonated automatically at optimal range. The improvement wasn't incremental, it was categorical. After Okinawa fell in June 1945, planning began for Operation Downfall, the invasion of the Japanese home islands. Intelligence estimates suggested Japan had preserved thousands more aircraft for kamikaze operations, defending the homeland. If kamikaze tactics at Okinawa had achieved 30% hit rates, the rates defending Japan might be higher simply due to shorter distances from airfields to targets, allowing more sorties per day. American planners knew that the invasion fleet would face the most intense aerial assault in history. The defensive plan relied heavily on lessons learned at Okinawa. More SCR-584 systems would be deployed. More anti-aircraft battalions would be equipped with the complete triad of radar, director, and proximity fuses. Training emphasized the importance of trusting the automatic systems rather than reverting to older optical methods. And crucially, the plan called for extensive pre-invasion strikes against Japanese airfields to destroy as many kamikazes on the ground as possible before they could launch. The atomic bombings of Hiroshima and Nagasaki in August 1945 and Japan's subsequent surrender made Operation Downfall unnecessary. The invasion never happened. The defensive systems prepared for it never faced their ultimate test. But the planning documents and training materials from that period reveal something important about how American commanders viewed the technological balance by mid-1945. They believed their defensive systems could handle even the most intense kamikaze assault Japan could mount, not without casualties, not without ships being damaged and men dying, but without the catastrophic losses that would force withdrawal or reconsideration of strategy. That confidence rested largely on the SCR-584 and the systems integrated with it. The confidence was justified. Post-war analysis of kamikaze effectiveness showed that attack success rates declined steadily throughout 1945 as American defensive capabilities improved. At Leyte Gulf in October 1944, kamikazes achieved hit rates around 37%. At Lingayen Gulf in January 1945, rates dropped to around 32%. At Iwo Jima in February, around 30%. At Okinawa from April through June, rates averaged 29% and dropped lower for specific periods when defenses were fully established. The trend was clear. Each campaign saw improved American defenses and declining Japanese effectiveness. Several factors contributed to this trend. American fighter coverage improved. Shipboard anti-aircraft systems became more numerous and better coordinated. Combat air patrol tactics evolved to intercept attackers farther from the fleet. But the single most significant technical factor was the deployment of SCR-584 systems to ground-based anti-aircraft battalions and the parallel improvements in shipboard radar fire control that drew on similar technology. The ability to engage targets accurately regardless of visibility conditions fundamentally changed the defensive equation. The Japanese never developed effective countermeasures. They experimented with chaff, strips of aluminum foil dropped from aircraft to create false radar returns and confuse tracking. The chaff was moderately effective against longer wavelength radars, but largely ineffective against the centimetric microwave radars, like the SCR-584. The Japanese generally dropped chaff about 30 miles from targets, which was too far out to interfere with terminal guidance when SCR-584 systems locked onto actual aircraft. Japanese attempts at electronic jamming of radar were similarly ineffective against microwave systems. The fundamental problem was that Japan lacked the technical sophistication to understand exactly what American radar systems could do, much less develop countermeasures. Japanese radar development had been hampered by inter-service rivalry, resource constraints, and a tendency to focus on long-term research projects rather than deployable systems. By 1945, Japan had numerous radar types in service, but none approached the capability of the SCR-584. Japanese commanders knew American ships and ground units had radar. They understood it provided detection and rough tracking. They didn't fully grasp that American radar could automatically track multiple targets simultaneously, feed real-time data to analog computers that calculated firing solutions faster than humans could think, and guide shells to detonation points with precision measured in feet. This intelligence gap meant Japanese tactical planning continued to assume night attacks would degrade American defensive effectiveness. Plans for defending the home islands emphasized maximum use of darkness and weather to conceal kamikaze approaches. These plans would have sent Japanese pilots into defensive systems specifically designed to exploit conditions where visibility was irrelevant. The casualties would have been catastrophic for both sides, but the asymmetry in defensive technology meant American losses would have been sustainable, while Japanese losses would have been absolute. The final irony of the Kamikaze campaign was that it accelerated American technological advantage. The desperate threat posed by suicide tactics justified unlimited resources for defensive systems. The SCR-584 program received absolute priority for manufacturing. Proximity fuse production scaled to levels that would have seemed impossible in 1940. Bell Labs received blank checks to improve the M9 directors and develop follow-on systems. The very tactic Japan adopted out of desperation ensured that American defenses evolved faster than Japanese attacks could adapt. By August 1945, when the war ended, American anti-aircraft capabilities had reached levels that would have seemed science fiction 4 years earlier. Ground-based batteries could engage targets at 40 miles range. Tracking was automatic. Firing solutions were computed electronically. Shells detonated based on proximity to targets rather than preset timers. Human gunners loaded weapons while computers and radar did everything else. The transformation from Pearl Harbor to Okinawa represented one of the most rapid advances in military technology in history, driven by the convergence of radar physics, analog computing, and miniaturized electronics that few thought possible when the war began. The human stories behind this technological revolution often get lost in statistics about hit rates and ammunition expenditure. Men like Henry Abajian, who spent months touring forward positions in the Pacific, training gun crews who initially distrusted what they couldn't understand, who demonstrated night after night that the system worked until skepticism turned to confidence. Engineers like David Parkinson, who translated a dream about potentiometers into an analog computer that calculated faster than trained mathematicians. Physicists like Lee Davenport at MIT's Radiation Laboratory, working 18-hour days to turn British magnetrons into practical fire control radars. Technicians at Sylvania and other contractors who manufactured 70,000 proximity fuses per day, each one a miniature marvel of engineering that would have been impossible to mass-produce 5 years earlier. These were the people who won the invisible war. The war where victory was measured in microseconds of computing time and degrees of radar accuracy. The war where success meant destroying aircraft that pilots and gunners never saw with their own eyes, guided entirely by electronic signals bouncing off metal fuselages miles away. It wasn't the kind of warfare that generated dramatic photos or inspiring propaganda posters. A radar operator watching a green dot move across a screen wasn't visually compelling, but that green dot represented mathematics defeating tactics, technology defeating courage, and industrial capacity defeating desperation. Japanese kamikaze pilots were some of the bravest warriors in history. They accepted certain death as the price of attempting to inflict damage on an enemy they knew was militarily superior. Their courage deserves recognition even as their cause does not. But courage without technological parity cannot win modern wars. The kamikaze tactic failed not because the men flying the missions lacked commitment, but because American defensive systems had evolved to a point where even suicidal determination couldn't overcome the mathematical precision of radar-guided fire control. The final accounting shows approximately 4,700 Allied ships operated in the Philippine and Okinawa campaigns combined. Of these, Kamikazes sank 47 and damaged approximately 400. The casualty figures were significant. Thousands of sailors and soldiers died or were wounded, but measured against the scale of operations and the intensity of the attacks, the defensive success was remarkable. Japanese commanders had launched thousands of kamikaze sorties, expecting to sink hundreds of ships. They achieved a fraction of their objective. American forces remained in place. Invasions proceeded. The defensive systems held. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The SCR-584 radar continued in service long after World War II ended. The system was adapted for various military applications through the 1950s and remained operational in some places into the 1990s. Modified versions tracked artillery shells in flight, detected vehicles, guided fighter aircraft to targets, and provided early warning of missile launches during the Cold War. The basic design principles, microwave radar with automatic tracking integrated with analog computing for fire control, became foundational for every subsequent generation of military radar systems. But the system's greatest legacy isn't its longevity. It's what it proved about the relationship between technology and warfare. In September 1940, when Eddie Bowen carried British magnetrons across the Atlantic, the idea that radar could automatically track and destroy aircraft seemed like science fiction. Most military officials dismissed it as impossible. The engineering challenges appeared insurmountable. The integration requirements between radar, computing, and weapons seemed too complex to solve on wartime timescales. 5 years later, teenagers fresh from basic training were operating these systems in combat, destroying aircraft they couldn't see during battles that decided the outcome of the world's largest war. The speed of that transformation was unprecedented. From laboratory prototype to combat deployment in less than 4 years, from skeptical initial tests to mass production of over 1,700 systems, from theoretical concept to proven battlefield effectiveness against the most difficult targets in the most intense combat conditions, the Manhattan Project gets remembered as World War II's greatest technical achievement. The atomic bomb ended the war, but radar won it. That was the assessment at MIT's radiation laboratory, and history has proven it accurate. The Kamikaze campaign represented Japan's last desperate attempt to inflict casualties severe enough to force American negotiation rather than invasion. It failed, not because Japanese pilots lacked courage or commitment, not because Japanese tactics were fundamentally flawed, but because American defensive technology had reached a point where even suicide attacks couldn't overcome the precision of systems that turned darkness into irrelevance and human limitations into automated advantages. The invisible electromagnetic waves that guided SCR-584 fire control created barriers that no amount of courage could penetrate. When Technical Sergeant William Henshaw watched that first radar contact appear on his screen in January 1945, he was witnessing the culmination of 5 years of scientific innovation compressed into desperate timescales. The British magnetron that made microwave radar possible, the MIT radiation laboratory that turned physics into engineering, Bell Labs that translated radar tracking into automatic fire control, Carnegie Institution that miniaturized radar into artillery shells, industrial contractors that manufactured impossible things in impossible quantities, and thousands of scientists, engineers, and technicians who worked through the war believing their calculations and prototypes might save lives. They were right. The mathematics of aerial warfare that seemed so hopeless in September 1940, when it took 20,000 shells to destroy a single aircraft, had been fundamentally transformed by August 1945, Radar-guided anti-aircraft fire was destroying targets with ammunition expenditures that would have seemed magical 4 years earlier. The transformation saved thousands of lives, American sailors and soldiers who would have died from kamikaze attacks that darkness once would have concealed survived because microwave radar saw through darkness as easily as daylight. Japanese pilots who might have survived to see their families again died because they flew missions against defenses their commanders didn't understand. War is ultimately about mathematics. How many ships? How many aircraft? How many shells are required to achieve objectives? How many casualties are acceptable to continue operations? The side that optimizes these mathematics more effectively usually wins. From Pearl Harbor to Okinawa, America optimized the mathematics of defensive air warfare through technological innovation that Japan couldn't match. The SCR-584 radar, M9 director, and proximity fuses turned the mathematics of anti-aircraft fire from a game of probability into a science of precision. That precision broke the back of the Kamikaze campaign. Japan never expected American ground-based defenses to guide 90mm shells into kamikazes at night with accuracy that made darkness irrelevant. Japanese tactical planning through 1945 continued assuming night attacks would succeed at higher rates than daylight attacks. That assumption was wrong. By the final months of the war, SCR-584 systems were destroying aircraft at night, with effectiveness rates that exceeded daylight operations using optical fire control. The technological advantage was complete. The electromagnetic spectrum had become a battlefield where America held overwhelming superiority. And in that invisible battlefield, measured in megahertz and microseconds rather than miles and minutes, the outcome of the visible war was decided. Not by the courage of warriors, though courage was abundant on both sides. Not by the righteousness of causes, though history would judge those differently, but by mathematics, by physics, by engineering, by the accumulated scientific knowledge that let one side see and strike with precision while the other flew blind into systematic destruction. That was the reality of modern warfare by 1945. That was what the SCR-584 radar proved over Pacific skies. And that was why Japan's last desperate tactic failed against defenses that turned night into a weapon American gunners wielded with mathematical certainty. The green dot on the radar screen represented more than just an aircraft. It represented the culmination of human ingenuity applied to the oldest military problem, defense against aerial attack. It represented 5 years of impossible deadlines met through sheer determination. It represented British desperation that crossed the Atlantic in a sealed black box. It represented MIT physicists working until exhaustion. It represented Bell Labs engineers who dreamed solutions and built them. It represented industrial capacity that could manufacture 70,000 miniature radars per day. And it represented the end of an era when darkness provided concealment and courage could overcome technological disadvantage. When American forces prepared for the invasion of Japan that never happened, they did so with confidence that their defensive systems could handle whatever Japan threw at them. That confidence was justified by Okinawa, by the Philippines, by hundreds of nights when SCR-584 operators watched green dots approach and guided automatic fire that destroyed aircraft no human eye could see. The invasion didn't happen. The atomic bombs made it unnecessary. But if it had happened, American ground-based anti-aircraft defenses would have been ready with systems that had proven themselves in the most intense combat of the war. That readiness represented the invisible victory. The victory of physics over tactics, mathematics over courage, engineering over desperation. The victory that saved lives by ending battles before they could fully develop. The victory was measured in aircraft destroyed at 40 miles range by shells guided through darkness. The victory that Japanese commanders never fully understood because they never grasped just how completely American defensive technology had evolved beyond anything their pre-war planning had anticipated. The SCR-584 radar won no dramatic battles by itself. It didn't sink enemy fleets or capture territory. It didn't make headlines or generate heroic narratives. But it did exactly what it was designed to do. It saw through darkness. It tracked what couldn't be seen. It guided weapons to targets with precision that made the routine impossible. And in doing so, It helped win the war by making Japanese tactics unsustainable, one green dot at a time, one calculated firing solution at a time, one proximity-fused shell detonating at optimal range at a time. Mathematics defeats determination. Technology defeats courage. The future, defeating the past, measured in microseconds and megahertz across Pacific skies that Japan thought darkness still possessed. They were wrong. America owned the darkness, and the price of that invisible ownership was written in the wreckage of aircraft that never reached their targets, destroyed by gunners who never saw what they were shooting at, guided by radar that made night as transparent as day and impossible as routine as mathematics.